So we just mentioned about the definition of Cij, right? So now let's try to consider the definition of Cij recursively, okay, or however you want to call it, like incremental thinking or recursive thinking. Okay, your Cij, okay, if the last character of this prefix from x and the prefix from y, if their last characters match, okay, then your Cij should be Ci minus 1, j minus 1 plus 1, right? Okay, 如果你现在这两个的那个 prefix， 那么最后一个字是一样的，那你这个最后那个字一样，你可以把最后那个字一样当做一个，一定会加一嘛，那就把前面那个 Ci minus 1 j minus 1那个最长的那个LCS 的长度再加一 ，right？ But if unfortunately there's no match, then okay, your Cij should be Ci minus 1 j or Cij minus 1, whichever give you a longer common subsequence. Okay, in other words, like the bigger one of these two, right? If we try to represent this in pictures, okay, in the picture, as a picture. So when case xi equal to yj, okay, if these two elements are the same, then the longest common subsequence, okay, should be whatever we have, the longest common subsequence from here and this plus one additional character, right? Okay. So we want to prove this, okay, a little bit formal. Okay. In the case xi equal to yj, okay, we want to prove Cij equal to Ci minus 1 j minus 1 plus 1. If xi equal to yj, okay, we want to prove that. So let's assume the LCS, okay, the prefix of x from 1 to I, the prefix of y from 1 to j is z 1 to k. This is the longest common subsequence. Okay, this is a string. This is a string. Okay, where because this is that zi 1 to k is a string. So Cij, okay, equal to k, the length of k. Okay. Then zk equal to xi, okay. It must be the case, okay. Otherwise, if zk if the last character does not come from this match one, okay, think about this. If that means like a z from 1 to k, okay, 这个 longest common subsequence， 如果这个最后一个字不是从这一个字来的，就是它是从这边来的，那你可以把 z extend， 你把这个加到，再把这个字加上去。You could extend the z for one more character. Then obviously z wouldn't be the LCS of, no, wouldn't be LCS here, no, right? 这是本正法，就是我们先讲，你先 claim，we first claim the no, the x prefix of x, okay, from 1 to I, the prefix of y from 1 to j, if these two characters match, we say their LCS, the last character must come from this matched character. If not, then we could append this matched character to this LCS to make this LCS even longer. But it shouldn't be the case, right? Because LCS is supposed to be the longest common subsequence. If you can make it even longer, it is not the longest one, right? So this is like a contradiction. So up to here, we already proved the last character of this LCS. The last character must come from this matched character. So this Z1 to K minus 1 is common subsequence of X1 to I minus 1 and Y1 to J minus 1. Okay? Because, well, the last character comes from that matched one. Okay? We get rid of that. So the other part of this common subsequence must come from the previous character of this prefix, right? So that's pretty much this. But is this one the longest common subsequence of these two prefixes? 它是最长的吗? We also need to prove that. Otherwise, this formula wouldn't hold, right? Because Ci minus 1, J minus 1. This C means the length of the longest common subsequence. Okay, but now we only show that this is like the Z from 1 to K minus 1 is the common subsequence, but it may not be the longest. So, okay, so we claim this must be the longest common subsequence of X from 1 to I minus 1, Y from 1 to J minus 1. Why? Because if not, if W is a longer common subsequence from these two prefixes, if it is longer one, say longer than K minus 1, this W, the length of W is longer than K minus 1, then, okay, we can just append that last character, the match character, to the end of W to make this even longer common subsequence. Then this one, right? Then this one. Then this one. But it is, again, this is wrong. Because this one is at least one of the longest common subsequence. So length wouldn't be the W concatenate, the W 连上 ZK. It shouldn't be longer than this one, right? It shouldn't be longer than this one. Okay. It's a common subsequence of this one, and with the length longer than K, but this again is not possible. It is contradiction. So that means, okay, the Z1 to K minus 1 is the longest common subsequence of X, from 1 to I minus 1, Y from 1 to J minus 1. So in other words, this formula is true. This formula is true. The top one is true. Okay. And in case if there's no match, so this one is true. Okay. In case when they are not, I mean the last character of these two prefixes does not match, it's relatively easy. Okay, because like you have this longest common subsequence. Okay, either the whole thing comes from the previous one. I mean you exclude like the last character of the first prefix, or it comes from we exclude the last character of the second prefix. This discussion is will be similar and much easier than the previous case. Okay, in this case we need to use like a two contradiction proof to show it is like that. But the other cases are much easier. Okay. So if you understand this recursive formula, okay, that's the key of dynamic programming. Dynamic programming, okay, there are two important principles out there. The first principle is an optimal solution to a problem. Of course, it's an instance of a problem. Okay, contains optimal solutions to subproblems. So, for example, here, when we want to find the longest common subsequence of a larger prefix, okay, of these two sequences, okay, you will find that, okay, the solution actually lies in, a shorter prefix, okay, depending on, if the last character is two prefixes, they match or not. If they match, then it's the first case. If it does not match, it's from the same case. But regardless which one it is, okay, obviously we are able to, reduce the problem to a subproblem, but still use the same optimal solution, okay, from these subproblems to construct the solution for a larger problem, right? So we have this optimal substructure. This is very important. Okay, any dynamic programming problem must have such a property. So if Z is LCS XY, then any prefix of Z is an LCS of certain prefix of X and a certain prefix of Y. That's what we meant here. Okay. So, with that recursive formula, we could easily write, you can convert that recursive formula into a recursive program easily, right? Like you learned that from your freshman, like a year. 计算机概论的接所是继承了膝盖。I mean, that course tells you, okay, if you have a formula, how to convert it into a formula, into a program, right? Here, of course, we ignore the base case. Okay, I mean, the base case is that this. Okay, so this is pretty much similar to identical to this recursive program. So there's really not much to discuss for this program. But one thing we need to talk about is the base case. What is the base case? What is the base case? The base case because we start from LCS n, right? And supposedly when you call this procedure, when you call this procedure, of course you pass the x and y, and initially you pass n to I, n to j, right? So yeah, and then we keep running this this recursive calls, with a smaller I and j value. Okay, eventually, okay, think about that. What would be the base case? It's going to be something like this. The C, well, actually, the base case is LCS. The X, Y is always there. The X, Y are always there. But with I and J keep decreasing, eventually the base case becomes like, for example, I 0, where I is not 0, but the other one, J, becomes 0. So according to our definition, okay, what should this one return? Somebody tell me. Because we want to return the length of the longest common subsequence from the prefix of x of length I and the prefix of y of length j. So in case like that, somebody tell me what answer should I return to actually. The other similar case will be right. So for these two cases, what should we return?其中就是空字串呢，你回传的最长的是什么 ？Zero, right? Zero, right? Any question with that? So, okay, if you consider base cases, okay, it should be at the beginning. If I or j is 0, return 0. Else, do this. Okay? 这可以很容易理解。Okay. 你就看你的 i 进来的 i 跟 j， 如果其中一个是零，啊，你一个字段都是零的，长度是零的，那你怎么可能会回传什么长度大于零的 longest common subsequence？ 就不可能嘛，就是零嘛，对不对？这个可以接受吧？对 ，This is the base case. This is the base case. Okay, and then the other stuff like we follow the recursive movement. Okay, so that's it. So in this recursive algorithm, what would be the worst case? Because the better case is that, you know, you have one procedure comes in and you call a subroutine, one subroutine, right? That's a better case. In other words, the last characters of these two prefixes match. Okay, so that's a better case because you only you only call one recursive call. But if the last characters of these two prefixes do not match, you will have to call two instead of one recursive calls, right? So the worst case is these two characters, two characters, at the end of prefixes, they do not match. Okay, in this case, your algorithm will evaluate two subproblems. So each with only one parameter decremented. I mean the reduction of your parameter is also becoming slow. So if we try to use a recursion tree to have a look, say initially your I is 7, your M is 7, N is 6. Assume the worst case happens all the time. Of course, this may not be the case, but let's assume the worst case nevertheless, because for us, the important thing is to want to see the worst case scenario analysis, the worst case complexity. So if the last character of two prefixes do not match, so we have to do 6, we have to do 7, 5. And if the last two characters from the two prefixes do not match, again, we need to do this. Probably one. So we see that the recursive call increases exponentially, right? Exponentially. So that's bad, right? That's bad. Okay. If you keep letting it go, if you keep this pace, when you go on through this pace, what happens is that what is the height of this tree? Because the height of this tree, you can see every time we decrement, when we go down one level, either the first either n decrement by 1 or n decrement by 1, right? So the height of this tree will be bounded by n plus n. Because each time you go down, you only decrement one of these two elements by 1. So eventually, as I said, the base case is that one of them to be 0, right? Okay, so an easy analysis is that the height is bounded by n plus n. But if the height is n plus n, and every time you see like with the recursive code increase like double, like twice, So obviously, this work, is going to, have a potential exponential time complexity, right? Okay, so that's bad, right? As I said, like we don't like, something that with a higher power, not to mention like exponential, right? We just don't like that. So this is bad. But don't lose hope. Don't lose hope. If you examine more closely, you will find something that you are able to take advantage of. Okay, what is that? You will find that many of the jobs are, executed, repeatedly. For example, you see this part and this part, they are identical, right? They are identical. What do we mean by 6-5? That means we want to find the prefix, the length of the LCS from the prefix of x of length 6 and the prefix of y of length 5, right? And this is the same meaning like that. This has the same meaning, right? We are doing exactly the same job. We are doing exactly the same thing twice. Not only that, you see like many of these places. For example, this 6-4. This branch, this 6-4, you see it appear here, right? 5-5. This 5-5 appear here. Right? So many same text gets executed many other, many times. So that causes this thing grows exponential. So what should we do? So an easy idea would be, hey, if you have computed this value already, don't do it again, right? If you have computed the answer already, don't do it again. So we call, before we talk about the solution, okay, this is the second property of dynamic programming. These two properties are very crucial. Okay, you have to have these two properties in order to call the algorithm the dynamic programming solution. Okay, the first one is like the optimal solution of the subproblem. Okay, is appear in the optimal solution of the whole problem all the time. The second important problem is that a recursive solution contains a small number of distinct subproblems repeated many times. That's exactly what happens here, right? A lot of recursive calls, are repeated many times. So the solution to this is the number of distinct LCS subproblems or two subscripts, two prefixes of length n. Okay, but think about this. Okay, if you consider all the possible different lengths that you could possibly have from two sequences of lengths n and okay, the possible combination of like different lengths that you could compute is n times n, right? Instead of exponential, it's this, right? 就是说你一个长度是 n， 一个长度是 n， 那你要从这里面 n 截断 n 截断来去算，对不对？那你长度你就只有从0，我刚刚讲过，0是 base case， 我们不考虑0，好不好？就1、2、3、4、5、6、8、8、8到 n 减1 n， 对不对？你就对第一个长度是 n， 你就只有 n 整长度可以考虑。同等，另外一个 n， 就1、2、3到 n 减1 n， 也只有 n 种长度可以考虑。那这两个 combination 就是 n 乘 n 嘛，我们排列组合都学过，对不对？所以这是所有可能的不一样长度的 prefix 组合就只有这个，对不对？所以呢， the idea is, if you have computed this combination already, don't do it again. We should memorize it. We should memorize it. What do we mean by memorize it? Well, just keep a table. Store the answer here. Okay, store the answer. In order to avoid, doing the same job again. So it will be like this. So you have a table of size n times n. This table is of size n times n. Okay. Initially, you put all the breadth meal. Okay. So you haven't given any value to that. So that's what we have. Okay. So you need to make sure that this table is empty. Okay. Then blah blah blah. If blah 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 blah. But here, okay. This part is the same. Okay. The only thing is you have this. You check if the table, if this combination has been done or not. You keep this table of size n times n. And when you call this recursive call, it will fill out this table for you, right? It will fill out this table for you. So if if somewhere like along this recursive computation, if Cij has already been filled, 它已经被填进去了，那这个就不会是这个嘛？那 Cij will no longer be needed, right? So you will just make use of that Cij value directly. Right? You only add one if statement, and then you are able to make use of that, table, whatever stored in that table. Okay? So that's it. Just adding one additional line here. All the other part remains exactly the same as the previous. Algorithm. We call such an approach memorization. Okay. And the time you take will be theta n because, as I said, all the possible combinations of either j will be very nice. So the space required is also theta n because you need that table, right? The table is of size n minus ij will initially will be like n, will be given an n. Okay, so you are doing this from top to bottom. But the other idea is you can do that from bottom up. Okay, what do you mean by this idea? So this is the table. Okay, initially, I mean, here, okay, you are actually doing this. You're starting from here, and then you try to, recursive formulate. Recursive formulate is like always that you start from the end, try to call like recursive call. You try to solve that some problem, small problems, and then do like the answer for you. So it's a little bit complicated, but that's top down. The bottom up will be what? The bottom up will be, initially, you start from this table. Everything is linear. Well, except that the base case. The base case is like here. It's zero. Zero. Okay, so you have zero here, you have zero here. Okay? And then, okay, you look at here. If the first character, A, B, right? A, B, there's no match. You look at the top and the left, okay? Whichever is B, you put it here, okay? So, for example, B is B, 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 okay, there's a match. So you just, this is zero, right? The diagonal is zero. You add 1 to something like that. Okay, B, C, there's no match. So 0 and 1, whichever is B, you do 1. B, B, okay. So again, B and this B, there's a match, right? So you just try to fill out this one by the diagonal plus 1, so it's 1. And so on. So you fill out this table, row by row. Well, you can do this column by column too. And the idea is the same. So eventually you are going to fill out the whole table. And the answer is the longest common subsequence here is 4. But this is a bottom-up approach. So the dynamic programming, okay, the algorithm, obviously, because every time dynamic programming, you will always see a recursive formula. So it is relatively easy to write a recursive program directly from that recursive formula. And then, make use of memorization concept to modify that one, okay, to make that program dynamic program. Yes, that's true. But, in reality, usually we do it the opposite. The bottom up. OK， 通常我们做的 program， 虽然说我们这边讲都是说，我们就是把它变成一个 recursive program， 然后我们把那个就是怎么讲，就是说加上一个 memorization 这样子，就这个就是 dynamic program。但是事实上在做 dynamic program 的时候，很多时候其实你是做bottom up， 就是你有个 table， 然后你是从下面去把这个 table 推往上。OK。概念上的确是这个样子，他们两个是 equivalent。OK， 那这样子讲，其实就从bottom up这样子讲，从个比较小的变到比较大的bottom up，这样其实是比较容易理解，也比较容易让你了解，为什么它的 time complexity 跟它的 storage complexity 都是 big data 等等。先休息10分钟，然后我们等一下继续，还没讲。
这没有想法，好好想。我做题老师这样。
大家听一下这边呢，现在我手上的是期中考的考卷。那如果大家看完考卷有想要分的话，今天就不可以把考卷带走，可以吗？如果到时候想要到我们的实验室跟助教讨论一下分数的话，会以实验室内部的考卷为主。如果你是带回家再带去实验室的话，我们就不会让你们更新成绩，可以吗？那这边大家可以来拿考卷。然后呢，之后如果大家想要分的话，请以那个 syllabus 上面公告的助教时间，就是礼拜三下午4点到6点这个时段才可以来实验室要分，可以吗？谢谢。